Hello and welcome to the third part of this separations process that I've been walking you guys through. Again, we have our agenda to the left, and we will be working through this bit by bit. So, just to kind of summarize what we have here, we're going to explain and arrive at a expression to be solved using the bubble and dew pressures for an ideal binary mixture. And then next, we're going to be doing a lot of code in this video. We can write a Python code for calculating the bubble and dew temperatures and pressures along a vapor and liquid phase, and then we are going to test those functions. Next, we're going to write another code to generate a binary VLE diagram for benzene and toluene at a constant temperature. Then we are going to repeat this process for a different pressure of 1 bar, and then finally we will generate a code to make a diagram for this constant pressure of 1 bar. I know that sounds like a lot, but we're going to take this step by step and make sure everyone understands what we do. So all of this is going to start with Raoult's law, just previously, so we'll write that down. Raoult's law, as we know, is XI/PI saturation equals YI/PI. And as we mentioned, we will be finding the bubble temperature, the dew temperature, the bubble pressure, and the dew pressure. So we can start with the bubble pressure, and to do this we will take down, we will just rewrite this Raoult's law as we did above. XI/PI sat equals YI/PI. Now, just so everyone's aware, there is technically a gamma value here, but as I've written here, for an ideal binary system, this gamma is going to be equal to 0, so we can just get rid of it. And then this YI here, excuse me, let me back up a little bit. Here we're going to add summation symbols. And now this YI value is going to be equal to 1, so we are able to get rid of it. So we simply have a, this is just P. Our answer for the pressure, the bubble pressure, is going to be P is equal to the summation of XI/PI saturation. And that is our first equation. Now for the dew pressure. So the dew pressure, we're going to take this same equation, XI/PI sat equals YIP. Again, we will add these summations, but now this time this will be equal to 1. So it is canceled out, and you arrive at P1 sat equals summation of YIP. Again, you want this P singled out, which gets you, needs to go away. Ignore. Okay. You have P equals P1 PI saturation divided by the summation of YI. And now we have the bubble T and the dew T, and these are going to follow the same process in which we have the same equation, XI/PI sat equals P, but now when you take the summations, this is all going to be equal to 1. And we are actually unable to use Raoult's law to solve this. So when we go into Google Colab, we're going to have to find the roots. We're going to call these roots fruits, but not the good, delicious kind, the kind that you have to code and that is not as enjoyable. And to do this, we are actually going to need the Clausius, I keep spelling that wrong, I think, Clausius-Clapeyron equation. Again, we'll get more into this when we're actually coding it. So now, before we go into Colab, I realized I accidentally forgot to mention two little things. The reason that this is not able to be solved through Raoult's law is because there is a little, it's dependent on the temperature here, so it's going to be a function. And then also the second thing I forgot to mention is that it's not just the Clapeyron equation, we're also going to be using the Antoine equation. Okay, so now let's step over to Google Colab and get to work. So as you can see, we have pulled in a library here from GitHub that we used in class. And the first line of code will be setting our variable p equal to props, and then we will use parentheses bracket. And then, as mentioned in the problem statement, we will be dealing with benzene and toluene. And this is, something is wrong. Here we go. There needs to be that. Okay, there we go. Benzene and toluene. And then we will add another line here in which we will define the bubble T. So we'll do define bubble P xt. Make sure we do our colon and indent, which I have mistakenly not done before. And then yp is going to be equal to x times our p dot p of vaporization as a function of T, which will also have the pressure as np dot sum of yp uppercase. And then we also needed to return values because we actually want to be able to spit back what we're looking for, and that will be equal to return p and yp divided by p. Now the next portion that we will be getting into will be the bubble temperature. And like I said, we had four different. We have the bubble and dew of the pressure and the bubble and dew of the temperature. And currently, I probably should have said this before I did the previous defining section, but we just defined bubble P. Now we're going to define bubble T. So we will add a line of new code. And I like to separate these out just in case there's an error. It's not all in the same section. Completely up to your choice. But so I'm going to go with bubble T now, and this is going to be the same. Actually, you know what? I'm going to change this. So we just did bubble P. Let's do dew P. So we worked with pressure in the last one. Let's just work with pressure again. So now we will do dew P, which is, if the last one was a function of x and t, this one's going to be a function of y and t. We will, oh, not f. What the heck? All right. Colon, semicolon. Okay. Now the equations for this one is going to be p vap is equal to p dot p vap of t. And we also have p, we're going to equal to 1 divided by np dot sum of y divided by p vap. And then again, we need to return values. That is what allows us to actually solve these problems. We want p, and we want y times p divided by p vap. Now we can run all to make sure everything's okay. And as of now, we are good, and we are able to move into our temperature values now that our pressure values have been taken care of. So now, like I said, we're moving into the temperatures, and this gets a little trickier because, as I mentioned, as you can see right there, we are going to need to use that fruit function. I always laugh at that. I think that's funny. So we will do bubble T, and this will be a function of x and p. Don't need a space there. And now this is where it gets a little bit tricky. So we'll do T sub 0. So our initial temperature is equal to np sum x times p dot tb p. Oh shoot. So funky. Sum, there we go. X times p dot tb. In there we want p. Okay. So now this is where we define our fruit function, which is going to be a fruit of t. And then we will, don't forget to add a colon there, and we will need to return the values of bubble p, not tp here, because it is going to be used as a function of x and t. And now this is just a NumPy input that will allow us to actually complete this fruit function. Optimize dot root underscore scalar fruit x sub 0 equals t sub 0 method equals secant dot root, not root scalar, just root. And then again, don't forget your return or else you will not get what you are looking for. X dot times p dot pvap of t. So now again, this is really important that all your syntax is correct. We're going to run it. I got lucky this time. I had no syntax errors, which is not always often. It is easy to always mix up maybe a parenthesis or a bracket or a period. So as of now, we are good, and we can move into dew temperature. Now, one easy thing here is that we are actually able to take all of this, put this here, change this to dew, and then now this is all going to be y. So everywhere that you see a y, or sorry, an x will be changed to a y, except down here in the optimize.root scalar section. Okay, so now we have our bubble p, bubble t, and dew t all set, and we were able to move from there. And so now that we have these four equations, we will be able to make a VLE chart. And then, if I remember correctly, we're going to make a VLE chart at certain temperatures and pressures, and then we will cap this all off by writing a Python code to generate a diagram for this benzene and toluene. No issue here. It was a very easy fix. I realized I accidentally had 0, 2, and 21. It is now 0, 1, and 21. And as you can see here is our graph, which is comparing the bubble pressure, which is going to be linear, and the dew pressure here. They start and end at the same point, but they obviously have a different course of getting there. So this obviously is our graph for constant temperature, and now we'll be able to go and do our graph for constant pressure. All right, so this is going to be very, very similar. So to save us some time, we're going to copy this code that we have from here, and we're going to minorly tweak it. But instead of constant t, this time it's going to be constant p. And then with this one, p is going to be equal to 1 bar, but we can just say that is equal to 1 e to the 5th. And then x1s, that is still good, except this is now ts because we're working with pressure. And then y1s for x, this is all good. So pretty much everywhere you see a p, we're going to swap out for t, and p will, so the t's and p's are swapping. That's what we're getting at. So this is ts, pulling from appendix t. And then again, this will now be bubble t, and dew t. This will be ts. This will be PS, sorry, TS. All right, let's run this. All right, obviously that is not what we're looking for. Give me a second and I will find the error. All right, I am back, and as you can see, I fixed this. I realized I had a couple syntax errors in this section here. Honestly, it took me a while to figure them out. I believe it was in here we had something defined incorrectly here. We were able to fix that, so we're actually getting plots now. And as you can see, it is pretty much the inverse of this. Not exactly, but with a constant pressure, the bubble temperature and the dew temperature are going to be decreasing as you get closer to 1. And whereas here, as you get closer to 1, they're going to be increasing continuously and continuously. So again, this was the plots made for the constant p and the constant t. And now finally we are to the last part, which we will be coding a x and y graph for benzene and toluene, and this will have a constant pressure and temperature. So let's start the coding process here. To start this, we will start with the same as usual, fig equals make underscore subplots. Now, first, there's going to be two lines in this. One will represent the concentration, and the other one will be rather linear, obviously out of parentheses. Now, this one is going to be fig.add underscore scatter. And the suggestion there is not correct, so we cannot use that. X is going to equal x1s. Y is going to equal y1s. And then the mode for this one is going to be equal to markers. And then we have to add the second line, fig.add underscore scatter, which will be equal to x equals brackets 0. And now, so as you can see, it's suggesting the rest of this, which is correct, but then we are going to need to delete that fig.update layout, all that stuff, and we're going to need to adjust the color so it's actually visible. So we'll do tab, which we will then delete this section out, which this is a case, kind of off topic, but the Google Gemini is very, very helpful. But it is not helpful if you don't understand what you need. It can't write it necessarily for you. It can in a sense, but for this one, you have to understand what your actual needs are in the process. You can't just let it write it for you because we also need the colors adjusted and we didn't need that end part. So if you understand the process, it is very, very beneficial. So red, green, and blue, we are going to do 100, 100, 100, and 0.5. We will do run all. Now, as you can see, these dots, I would rather these be lines, actually. It's okay, this is good. So as you can see, let's make this trace one darker. Let's make this 100 also, so it's legible. Okay, so as you can see, this curved line is representing the benzene and toluene at a constant pressure and temperature, and this trace 1 is giving you a point of reference. As it goes from 0 to 1, you are able to see this curved graph. All right, thank you for watching, and I will complete the last part now. Thank you.